Strategically located on Monbray Creek, along Spencer Gulf's world-leading aquaculture center, featuring 3D ocean, indoor aeroponic, and outdoor permaculture farming, Afia creates an oasis of food for 100,000 ounces.
Afia intersects Augusta Highway and Australia's Transcontinental Railroad, facilitating regional growth and trade.
The Transcontinental Railroad stops at Afia Station, where in jet incline and our vascular network system deliver goods and produce to our mixed zone, high-tech, industrial, commercial, and residential centers. Walking and biking paths and our gold standard bus rapid transit connect these centers to some of Afia's greatest landmarks, including the Museum of Agricultural Engineering, Monbray Permaculture Park, and Afia's underwater aquaculture laboratory.
Along with advanced transportation, Afia features sustainable power solutions for energy, water, and food production. Our buses run on carbon-sequestering algae biofuel, and Eurogan Falls powers our Cortex quantum computer, which coordinates our transportation network. Water turbines, artificial leaf, and other green technologies power our self-sufficient buildings. Ocean thermal energy and water FX use ocean temperature differences and concentrated sunlight to desalinate saltwater, drawn from underground aquifers.
Cleaned by carbon aerogel, stimulated with electricity, desalinated water supplements rainwater.
Biosystems engineers designed the biodigester at our sanitation plant, which converts liquid waste into drinking water and liquid fertilizer for our aeroponic produce. Wind and solar windows filled with nanofluid provide light, power Romanesco farms, dry our crickets, and grind them into a powder.
Afia relies on nature to produce much of our food. A biodigester at Afia's sanitation plant converts solid waste into fertile soil, which provides the biomaterial needed to make our permaculture parks grow. Salmon are farmed in the tidal-powered Nile Lagoon, while turbine-powered aquaculture and 3D farming in Spencer Gulf supplement our food production.
Sustainable urban environments require an abundance of locally produced, fresh, and healthy food to meet the nutritional needs of a large population, while minimizing environmental impact, including limiting the production of greenhouse gases, other pollutants, and the demand on land and fresh water. As the charts show, genetically modified Romanesco and cricket protein provide Afia's sustainable solution.
Crickets contain all 9 essential amino acids required by the human diet, have as much B12 as salmon, 15% more iron than spinach, and contain magnesium, phosphorus, and other essential nutrients. Crickets also produce a superior amount of protein compared to the land and water requirements of other competing proteins, and a fraction of the methane byproduct.
Staggering the breeding process allows for weekly generational harvesting in our 160,000 square foot cricket harvesting and processing plant, also known as CHPP.
Key considerations in our CHPP include quality control and environmental regulations regarding how crickets are raised and treated. To ensure nutritional value and quality taste, our crickets are fed chicken feed, a proven food grade for human consumption. Ingredients include recycled food waste that cannot be sold in grocery stores or restaurants.
Cricket larvae are obtained at Amunate University, where regular microbiological testings and genetic diversified breeding prevent biological and genetic diseases from harming our cricket population.
Crickets are always kept in high-density plastic troughs, which are thoroughly bleached clean of contaminants before reuse.
An Australian Department of Ag approved nanocoatings seal all containers, preventing dangerous BPAs from leaching into our cricket population.
Ideal growing conditions require crickets be kept at 90 degrees Fahrenheit, 90% humidity, climate-controlled environment before they're ethically harvested. A few hours at 32 degrees slows down their heart rate and puts them to sleep before the temperature drops to 0, painlessly killing the population. Frozen crickets are then moved to the solar dehydrator at the top of our plant.
Solar-paneled glass windows filled with nanofluid quickly and efficiently heat the conveyor line. Quality assurance regulations require moisture sensors to ensure the proper dryness before crickets are dropped into the hopper and ground into powder.
An autobagger beneath the grinder wraps the powder, which is loaded on the trains at the adjacent depot and shipped out to the world market, while drones deliver the powder to our city's major centers.
Cricket waste is an important fertilizer additive for Afia's Romanesco, grown aeroponically in high-density, nano-sealed plastic towers in our LEED-certified vertical farm.
Afia chose Romanesco because of its superior nutritional value compared to other vegetables, its visual appeal, and its overall pleasant, sweet, nutty taste.
Solar-powered pumps deliver a high-nutrient mist from a basin-stored reservoir, which maintains water temperature at 65 degrees and reduces the need for air conditioning.
Although requiring a larger startup cost than traditional farming, aeroponically grown produce requires 90% less water, stays fresher longer, and and yield 6 times more food per square foot of space.
Plentiful, healthy food serves as the foundation for our educated society. Ag Ed begins in elementary school and continues through AFIA's Ammunition University labs, where synthetic biological engineering produce our superfoods.
The founders of AFIA consulted big cricket farms in Youngstown, Ohio, to help them through the engineering design process. The problem was to determine the most sustainable protein with limited costs, environmental and otherwise. When brainstorming, we could immediately eliminate other competing proteins because of their unsustainability. Cricket powder had too many advantages to ignore, so we scaled up from big cricket farms numbers to ensure we could feed our population.
AFIA owes its success to a collection of agricultural engineering specialists who are critical to AFIA's food infrastructure. Civil engineers zone the city with the production, distribution, and security of food in mind.
In addition to the previously mentioned biosystems engineers, facilities and quality control engineers designed our cricket and Romanesco farms, while material engineers designed the solar paneled windows, which power our solar dryer and grinder.
Biochemical material engineers design the nanocoatings that secure our cricket troughs and aeroponic towers, as well as the carbon aerogel that desalinates our water. Geological engineers design the geoheating and cooling systems that maintain our farm's ideal climate. Finally, biodiesel engineers design the algae biofuel that powers the trains that deliver our produce to the world. Together, these engineers provide the solutions to AFIA's sustainable food infrastructure.
Regionally connected by a vast transportation network and designed to be a self-sufficient community, AFIA is a thriving model of urban sustainability.
Welcome to AFIA.
Which part of the engineering design process was the most challenging for your team and why?
Probably the most challenging part was the finding the best protein for our project. We had to compare the nutritional value, the amount of methane it caused, and what overall was the best solution. So we made graphs and charts, and cricket powder had too many advantages to ignore, so we picked that.
How long is the growing season for your city, and how long does it take to produce the crops that raise the crops and raise the animals for your city?
Our crickets we stagger the breeding process so we can weekly harvest each generation. So it takes I think it's about 3 weeks for the crickets to come up to full scale. And the growing season doesn't, it's endless because of the fact that we use indoor farms.
One of the elements that I remember from your earlier presentation was your solar orbs. Can you tell me what makes them better than a typical solar panel that most of us already know about?
The solar orb is filled with a nanofluid that both generates electricity and heat, and then it concentrates the sunlight onto a smaller, more efficient solar panel that produces superior amount of electricity.
Excellent, thank you.
Thank you very much.